Hello everyone, I am Alkesh. I'm a PhD student at Temple Robotics and Artificial Intelligence Lab at Temple University in Philadelphia, USA. Today I will be presenting my paper entitled Deliver, a system for LLM-guided coordinated multi-robot pickup and delivery using Voronoi-based relay planning. In this paper, we develop a system that we call Deliver. Deliver stands for Directed Execution of Language Instructed Item via Engineered Relay. The flow of the presentation will be as shown here in this slide. Let us start by introducing the project. Currently in warehouse logistics, such as in Amazon Robotics warehouses, the current state-of-the-art uses massive fleets of robots, around 750,000 robots. Their method is simple. One robot picks up an item and travels the entire distance to the destination. This results in high traffic congestion and inefficient long-range travel. In contrast, we propose Deliver, from long haul to relay. Deliver enables relay-based planning where robots stay in local zones. It connects local robot zones via sequential handovers at the shared boundary. Our contribution enables robots to travel less, stay in their zones to avoid cross-map congestions and collisions. Let us look at a graphical representation of our motivation behind this project. Imagine this. You are lying comfortably in bed and you need a glass of water. And then you ask a robot to bring it. Imagine your robot actually understands this command and delivers it to you. And what if you had more than one robot working together like a relay team? One in the kitchen picks up the glass, hands it to another robot midway, and the last one decides to take the glass of water and bring it to you. That's exactly what Deliver does. Let us now formalize the problem. Our objective is to enable language-instructed sequential planning for multi-robot pickup and delivery via relay-based execution. The setup is, we use natural language command C as an input. This can be any natural language command. For example, bring a glass of water from the kitchen to the bedroom. This example is used extensively throughout the presentation. Then we have a team of robots operating in a shared workspace. And our goal is to coordinate these robots to identify the pickup, drop-off, and relay locations. We then assign a relay sequence executing the delivery. Let us now look at the system overview. How does Deliver work? Allow me to give you a graphical illustration of the framework. A user gives a command like
Bring water to the bedroom from the kitchen.
Deliver then extracts the pickup item, pickup location, and delivery location. Before the task begins, the robot partitions the environment into Voronoi regions, assigning each robot its own area of responsibility. Finally, each robot executes its assigned segment through a finite state machine, coordinating handovers and executing relay. Let us now discuss the methodology of the system. A user's command is transcribed by the Google Speech API and interpreted by Meta's Llama 3 model, which extracts the pickup item, pickup location, and delivery location. Before the task begins, the robot partitions the environment into Voronoi region, assigning each robot its own area of responsibility. Using the output from the LLM, the system then identifies pickup robot, delivery robot, and the active relay agents. It computes the handoff point along the shared boundary and finally executes its assigned segment through a finite state machine, coordinating handover using LED signals in real-world experiment. Now that we have understood how the system works, let us look at some robots in action. So, do you want to see Deliver? In this example, 3 Turtlebot 3 robots operate in a semantically labeled environment with kitchen, living area, bedroom, and storage. Watch how my LabMate Jared issues a natural language command.
Please go to the kitchen, pick up the package, and deliver it to the bedroom.
The system understands the instruction and coordinates the relay automatically. To visualize the handoff, we will be using LEDs. Watch how the first robot moves to the pickup location, and when it picks up the object, you will see that its green LED turns on. There you go. Now it moves to the handover location, and you can see that it will indicate its readiness by turning on its blue LED. When the blue LED is turned on, the other robot grabs the package indicated by green LED and moves to the next drop-off location. The handover is repeated, and you can see finally the robot reaches its final delivery location. In this next experiment, we will showcase the efficiency of our system. While we have 3 robots in the pool, our system will only use 2 active robots, demonstrating that our system takes care of energy resources and other efficiency factors, as was discussed in the methodology section.
Please pick up the package from the kitchen and bring it to the living area.
In this video, you will see that there are only 2 robots involved because the kitchen area and the living area are nearby, and there is no need for involvement of the third robot, which is on the opposite side of the layout. The first robot reaches the kitchen now, picks up the package, hands it over to the second robot, and now the second robot goes to the living area. To demonstrate the efficacy of our proposed framework, we also conducted some simulation study. We found that while the total mission length increases slightly due to handover detours, the burden is distributed effectively, preventing any single robot from traversing the entire map. This results in a significant efficiency gains. As the fleet size grows, the travel distance per robot decreases dramatically, achieving up to a 55% reduction in individual workload with 10 agents. As was demonstrated in the second experiment, the system is highly selective. In the video, we showed that even though we had 3 robots in the pool, only 2 were used. In simulation study, we used a pool of 10 agents, and we found out that roughly around 3.5 agents were activated on average, which means only 35% of the total agents were being utilized, leaving the majority of fleet free for other tasks. This helps us save on fuel, this helps us save on energy, and leaving less footprint behind. In conclusion, we proposed a novel framework called Deliver, a language-instructed framework that converts high-level commands into sequential multi-robot relays. We utilized Voronoi-based partitioning to constrain agents to local zones, reducing traffic congestion and interference. Empirically, we demonstrate a 55% reduction in individual travel distance with effective workload distribution across large fleets. I would like to extend my sincere thanks to my advisor, Dr. Philip Deems, and to my lab members, Jared, Alex, Kevin, and Malin. Without your help, this work wouldn't have been successfully completed. I would also like to thank National Science Foundation for funding this work. A special thanks to IEEE Industrial Electronics Society and the Society of Instrument and Control Engineers for their recognition of this work. Thank you so much for your attention. If you have any question, please reach out to me in my email address alkesh@temple.edu. You may use the QR code scanner of your phone to read our paper. Thank you.